alkenes in general. So what do we mean? Two alkenes die. We can have tri, tetra, whatever, multiple alkenes, right? And the important ones are the 1,3 skipped ones, the conjugated ones, but there are different flavors, okay? So we can have 1,5 hexadiene here, which, the two alkenes are not right next to each other. By the way, we already did the nomenclature for dienes, alkadiene or alkatriene. Then you need the numbers in the front to know where the alkene is. Not a big nomenclature guy, but I'm not going to review that right now. But you can see this 1, 2, 3, 4, 5 hexadiene if you want to write out that. And what do we say here? We've got sp3, sp3, two methylene carbons, and then our sp2s are right here. So we call this an isolated diene, okay? Meaning those two alkenes react as if they were just simple alkenes, okay? You already know their reactivity. You can do Markovnikov or anti-Markovnikov additions there. But we also have these, 1,3 butadiene, where we don't have any sp3 insulating saturated carbons in between. We have the sp2 right next to each other. And that's our conjugated one. Okay? And these are the ones that are going to give the 1,2 versus 1,4 addition. So we've already summarized 352 for you there. Of course, we'll get into the details of that reaction and the Diels-Alder. Those are the two new reactions here in chapter 16. But it's because it's conjugated here, and it's always 1,3 skipped, okay? Which begs the question here, can you have a 1,2 diene? What would that look like? Well, it would look like this. That's called alene. It's a known compound. It has a different hybridization now. We've talked about sp3, sp2 carbons. What's the hybridization right here in the middle of alene? What would it be? How many carbons is it bonded to? 2. So what is it? Is it sp2 again? No, that's for carbons bonded to 3 different things, right? Trigonal planar. This is linear. So what is it? SP. Very good. Someone said that with a lot of authority. I appreciate that. In fact, you can look at what that looks like in 3 dimensions here. It would have the hydrogens on the end here. There's 2 hydrogens here. Right? Remember, 2 hydrogens. There's no hydrogens on this guy. And because it's sp hybridized, you have 2 p atomic orbitals left behind. You see they're what? They're perpendicular to each other, right? They're 90 degrees to each other. That gives that linear effect. And they're not conjugated. They're electronically insulated from each other. It's the ones that are 1,3 that are right next to each other, right? So, you already saw the orbital there for the allocation. Well, here's what a conjugated 1,3 polyene is going to look like. It's going to look like that. And we need to look at some of the details of that now. Okay, so, what do we call this one? This is cumulated. These are much less common in nature or in industry. So we won't need to worry about those, but there might be a couple questions about them, the structure, whatever. They have different reactivity than the conjugated and the isolated. Isolated, you already know. Okay, it's the conjugated ones we need to go over. Those are called cumulated if they're 1,2 to each other. Okay, all right with that. All right, let's see. Let's get into a little more details here on the structure of our 1,3 conjugated thing here. So yeah, we've got pi bonds, right? We have 2 pi bonds here and here. Well, what's that right there? Is that also a pi bond? When we draw it here, we see the pi bonds here and here, right? But here we see a sigma. And I think that's the fundamental question now, okay? Let's see, what do you think? Does this have pi character, or is it just like a regular sigma bond? What do you think? Well, let's look at some data. give you some information here. Well, you know, a simple isolated alkene here like ethylene, the bond length here is 1.34 angstroms. An angstrom is 10 to the minus 10 meters, super tiny, right? Well, we know these numbers very accurately from X-ray diffraction data. We know what an alkene bond length is, 1.34. And, you know, you're familiar with it, right? The pi bond and everything, the pi star if they're out of phase with each other. Okay. It's flat, trigonal planar, right? Well, what about an alkane? If this thing has sigma bond character, what's the bond length of a typical alkane, sp3? Anybody help us out? Higher or shorter than 1.34? Longer or shorter? Longer? Yeah, what is it, 1.54? Okay, well, have we done X-ray structures on 1,3 conjugated polyenes? Yeah. So what's this distance here, bond length? What do you think? Would that say something about then the electronic character of that being a true sigma bond, isolated? Or will it be what? What do you think? Anybody have any ideas? Yeah. Yeah, it might be in between the two. The average would be 1.44, right? It's not quite that. It's 1.48. Okay, which you see that double bond character. So if we add in the shading here, or the phase of the wave equations here of the individual atomic orbitals, okay, and we're going to have to mix and match those and create the full molecular orbitals. And stay tuned for that. That'll be coming up on Wednesday. So if we have 4 atomic orbitals here, and here we're referring to the p atomic orbitals on each carbon, how many molecular orbitals are we going to create when we mix and match those quantum mechanically? And thank goodness we'll just pictorially, descriptive look at the quantum mechanics, but we create 4 molecular orbitals, okay? We'll have to create an array of molecular orbitals where we change these phases and have different amounts of nodes called, okay? Remember, these are wave equations, or psi. They're big, complicated mathematical equations. But you can already see, if we draw these all in phase, look, between C2 and C3, we have this in phase, right? What's that going to do to this bond length? It's going to shorten it, right? In fact, we could say, well, what is this really? We could, by resonance, do this, right? And what would that look like? Well, yeah, we'd have charge separation. That's not very good. But look at this resonance structure. What do we have here now? Double bond, right? So you can already see some things there. Let's get into that later. We'll do this, like I said, on Wednesday. We'll do the full MO description there. Let's get into some reactivity here. Let's look at some more allyl cations. They're kind of the important thing. Let's take a reaction here that you already know. Let's do ethanol and tert-butyl chloride. And how about this tertiary chloride? Same thing, ethanol. Let's look at the relative rates of these reactions. You already know what the product is. It's going to be ethyl ether. And the product here is also going to be an ether. We're going to have to see. It might be a couple different things there where the ether could go on there. But which one's going to be faster here? Well, here's our step, right? Sn1 ionization here. Intermediate's going to be that tert-butyl cation. Well, that's going to be good. And then attack there and loss of the proton gives us the product. But what about here? Let's see. It's going to be this. That's also a tertiary cation. But what else is it? It's allylic, right? It's an allyl cation. Okay? And we've got a resonance structure there where we've got this. All right? And that resonates between a tertiary, and a primary, but it can delocalize those electrons, right? What about the relative rates? That's why I point this out. Well, you can normalize this rate to 1 over here. And this rate over here is 123 times faster. Why? Because the slow step is what? Loss of the chloride to give the allyl cation. Why is this one so much faster? Because of this allylic resonance, right? And it's not only that, it's the products too. So when we do this reaction actually in water, sorry, I've got the data for it in water. If you do this guy here, this starting material in water, you get out this product, that alcohol plus this alcohol, and you get an 85-15 mix of those two products. So yeah, we're getting different products, right? With an alkene, we just got Markovnikov addition, right? The more substituted alcohol. Well, look at this. We're getting a lot of this primary alcohol. Why? Well, that's an allyl cation right here, right? Okay, one other thing to point out here. You can take this allyl chloride, and I'm using that term again, allyl chloride over there for the starting material. This is just a tertiary chloride. This is not allylic, right? This allyl chloride is different than that one up on the right here, right? These are constitutional isomers, different isomers of each other. Guess what? They react at the same what? Rate. They're both 120 times faster, 23 times faster than this guy. And guess what? They give the same distribution of product. Okay? When this guy ionizes, what happens? It gives the primary allyl cation here, which is in resonance with this guy here, right? And that's the slow step. And that gives this same allyl cation and then a different nucleophile. Well, I'm showing the nucleophile with water. That's the one where I have the ratio, but it's similar. It's a little faster reacting than this one. It's a little bulkier, but don't worry about that. The key thing here is in water, this allyl chloride and this allyl chloride are the same that way, which is pretty amazing stuff. Yeah, so next time we'll do the MO theory, and we'll get into the details of the 1,4 versus 1,2. And zoom into office hours. Make sure you know your time for your recitation. We've got those up there. Tyler, I know, and Jesher and these guys, Braden, Gannon, who was here a minute ago, and the other TAs, yeah, will help you out with that. So very good. Email me with questions. Sorry we didn't get too much questions back and forth, but we'll leave it right there, and we'll see you next time. Okay.